What we're going to do today is we're going to review just briefly what we talked about on Friday before Thanksgiving. We're not going to go real deep into the X-ray creation because where we are right now is with emission from the X-ray tube. So you know there are two different ways to create X-rays. It's brims, which constitutes statistically they say 85% of the beam. And then we've got characteristic, which they say statistically is 15% of the beam. Brims occurs whenever we have a loss of energy because of a projectile electron gets close enough to the nucleus of the atom to lose a lot of energy. And it occurs at a distance from the nucleus as well, but the further away from the nucleus it is, the lower the energy is going to be. So what we're most interested in is what gets close enough to the nucleus to be within the diagnostic range, and that is even a smaller portion of the overall energy that we create in X-ray beam. Characteristic, as we're going to look at today, we create characteristic in a lot of different energy levels, and the characteristic that we're most interested in is the highest possible energy of characteristic, and that would be 69.5 kVp, so that's the only one that we're going to focus on. We're going to look at the entire characteristic spectrum, and in that observation of the entire spectrum, I can see how possibly as much as 15% of the X-ray beam is at the target characteristic, but in as much as just the energy level that we use at 69.5, the numbers don't, the math doesn't math for me. So I can't see 15% of the X-ray beam being at 69.5, but overall possibly with all the different levels of characteristic X-rays. But again, the only one we focus on is 69.5, the only one that I will test you on is 69.5. So what we talked about then was, I'm going to draw 4, maybe 5. I'm just going to draw 4. I'm going to explain what you're seeing in the 5th one in the book. Brim spectra. All right. So we talked about on Friday that X-ray creation at the face of the target is going to be primarily low energy X-rays because what we're shooting are electrons, which are infinitely small, at the nucleus of the atom, which is infinitely small but less so than the electrons, right? And the chances of those electrons getting close to the nucleus of the atom to create a high energy X-ray photon is very, very low. So we said that X-ray creation at the face of the target looks something like this, where what this represented was the energy level, and energy in X-ray is kVp, so that's the kVp level that we set. And for, just bless you, for this particular thing, we're going to say we're at 50 kVp, okay? So then we said that the X-ray beam, to get off of the target and get to the patient, it has to go through a lot of stuff. And that lot of stuff has to add up to 2.5 millimeters of aluminum equivalent, right? So it's got to go through some stuff to get to the point where we can legally expose the patient to that X-ray beam, right? So it's got to get up to that point. So the first thing it goes through is the glass and the glass envelope. So that's going to filter out a portion of it, right? And so what we did there is that we eliminated the lowest energy X-ray photons, okay? So I use the analogy of, test grades. So if you have test grades that go from 0 all the way up to, this says 50, but let's say 100, and I eliminated the ones that were 0, 1, 2, 3. Those scores were eliminated. What happens to your average? It gets higher, right? So it doesn't get a whole lot higher, but it gets higher, right? So what happened when it went through the glass is we eliminated some of those low energy X-ray photons. So now how many test scores do you have? You had 50 to begin with. Now how many do you have? less than 50, right? So you lost tests, right? But you got a higher average. So you lost some numbers and you got a higher average. So if it goes through the oil, and then the next thing it goes through, or I'm sorry, it goes through the envelope, and then the next thing goes through is the oil. The oil, you know, I used the freshman 15 thing that people kind of went, telling us we're getting fat. Well, you know, welcome to the club. It's going to absorb some x-rays as well. And so what happened then? Well, when it went through the glass, we lost 0, 1, 2, 3. Now we lost 4, 5, 6. Your test grades were 4, 5, 6 on this end. What happens to your average? It goes up again. It goes up again, but what happens to the number of tests you took? It goes down. So we lose numbers, we increase average, right? So the next thing it goes through is the window or the port. And some textbooks may refer to it as a port, and that's in the protective housing. So again, that's going to be glass, maybe a different thickness of glass. So it's going to absorb some x-rays too, right? So now we lost even more tests, but they were low energy tests. Nothing happened at the peak energy, right? Nothing happened to your highest test grade average or your highest test grade, but what happened was that you lost more of the low energy test scores. So again, what happens to your average? It goes up, but your numbers of tests go down, right? So then the next thing it goes through is the back side of the mirror, or the mirror itself. And a mirror is glass, of course, but it also has a metallic backing to it. We know metal absorbs a lot of x-rays, so it's going to absorb some more x-rays, and it gives us a spectrum that looks kind of like an elongated bell curve now, and what we lost again was a number of x-ray photons. So the peak of this bubble decreased. It decreased, but it pushed towards the high energy side. We got a higher average. Now, if that got us to 2.5 millimeters of aluminum, we're golden. It probably did not, so at some point in between the tube and the mirror, they're probably going to add some more filtration. And again, what that's going to do is it's going to decrease the height. So the height of the bubble goes down. This is filtration. Anytime we add more filtration, the height of the bubble goes down. The bubble just represents the numbers. The peak of the bubble represents the average, and on each one of these, two things to remember about the average is the average, when we add more filtration, pushes towards the high energy side. The peak of the bubble represents that average, and that average is always right around 1/3 of the peak energy. Okay? I always do this. Let's make the numbers easier. We'll call it 60 kVp. So on this X-ray beam, what is our average energy? It's about 20, right? It's about 20. Okay, so if we add more filtration, though, it's going to change that a little bit. What's going to happen if, let's say, the tube ages? As the tube ages, what happens? We've got tanning. Very good. We've got tanning of the X-ray tube, which is laying down a layer of filtration, tungsten, on the inside of the tube, and therefore we're going to have more filtration, right? So as we get more filtration, what's going to happen is that the height of the bubble is going to go down some more. The average is going to increase, so it may be 2.5th, right? However you would pronounce that. Anyway, so the average increases, the peak of the bubble decreases. Every year, your physicist is going to come in, hang on just a second, and measure the amount of output from the X-ray tube. And they're going to have to adjust it a little bit. So every year that the tube ages, because you're coating the inside of that X-ray tube with tungsten, your filtration is going to increase. Okay, now remember, we've got two different types of filtration. We have additive filtration and we have inherent filtration. Inherent filtration is this plus tanning. Okay, So tanning is inherent filtration, is kind of an increased inherent filtration. I want to say added inherent filtration because that, sounds kind of contradictory. It's increased inherent filtration because of the age of the tube. So what we're going to get is a decrease in the height, decrease in the number of x-rays that we create. It's going to further push it towards a high energy side, and we're going to get higher average, okay? So we can filter the beam enough to where eventually the brim spectrum looks like something more like that, all right? At that point, what we've got is an x-ray beam where all energies are pretty similar. We lose some contrast, we lose, differential absorption decreases, and that's just not ideal. So we're never really going to have a beam like that. Our brim spectrum is always going to be that elongated bell curve, kind of like what we're seeing here.
Yeah, so as the tube ages and we get more tanning, that's also going to create arcing as well. So how does that affect the quality of the beam looking at?
Well, it's not really, because as soon as you get arcing, the tube is in short circuit, and you got to replace the x-ray tube. So yeah, but you're absolutely right. As we increase tanning, especially if we're utilizing a glass envelope, then we'll get into the problem with arcing. So arcing is a very common cause of tube failure, owing to tanning, which is caused by heating, right? Everything goes back to heat, but it's going to immediately kill the x-ray tube. It's in short circuit at that point.
Once it arcs the first time, it's just done.
Yeah. That's what they tell us. I've never experienced that. I'm not proud of this, but I was trying to, demonstrate something for a student one time, so I maxed out the KVP, got a loud pop out of the x-ray tube. Yeah, and I thought, oh man, I just killed that. I worked night or evening shift at the time, and this was an ER x-ray tube. Our only high frequency ER x-ray tube. We had high frequency next to single phase. I got that pop and I thought, I just really messed up. But it continued to make x-rays. What that pop was, I don't know. It could have been arcing. And if it was, then arcing clearly does not, because we used the tube for the rest of the night, arcing clearly does not always instantly kill the x-ray tube. Was it arcing? I don't know. I don't know, but I will never do that again. So filtration decreases the height and pushes towards a high energy side. We get an increase in average. The more filtration we add, be it from tanning or if we just added more filtration, it's going to continue to do that. It's going to continue to push it towards a high energy side. We have a decrease in average. Now, the reason I bring up the physicist is because, the average tube energy for, the properly filtered x-ray beam is about 1/3. All right, so that 20 kVp will penetrate surprisingly more than what you would expect it to penetrate. You're only using 60 kVp on hands and feet, right? You probably get through toes with, some of these 20 kVp x-ray photons. So since we remove those, though, then the tube output decreases. So the physicist is going to have to come in and they're going to have to tweak it. Every year they measure with a little, it's what they're referred to as a digital mass meter. They'll put it on the table, make an exposure on it, and read how much the x-ray tube actually put out. And if, let's say they will just use mass, as an example. If they set 5 mass and they get 4.5 mass, then they've got to go in, they got to tweak it a little bit and bring it back up, the tube, not the meter, and bring it back up to 5 mass. Okay, so every year they do that. And what we're left with in that case is a more filtered x-ray beam that is still going to put out 5 mass. Right? It's more penetrating x-ray beam, it's safer for the patient, but it is actually harder on the x-ray tube. And we'll walk through that before. Since we're creating more x-rays to compensate for the filtration, we create more heat, which creates more filtration, which creates more heat, and it just accelerates the death of the x-ray tube. Now I'm going to combine chapter 8 and 9 here, because chapter 9, if you looked ahead at chapter 9 refers to really kind of intensity. What happens with intensity with these changes? Okay, so what is intensity? In radiology, what is intensity? You know, I struggle with that too. I wanted to make KVP so badly, I wanted to make KVP intensity. And I'm going to really screw you up here in a minute, because it does control intensity, much more so than the thing that we use to control intensity. Intensity is numbers. Okay, what controls numbers?
Mass.
What do we use to control numbers? Is mass, right? So mass. All right, so intensity. So what happens with our intensity? If intensity means numbers, what happens with intensity as we increase filtration? We decrease intensity, right, right. Okay, so then let's look at mass, since we're there. We got mass, and I'm not gonna run through all the filtration's already created. So if we set a technique now, let's say we're at 60 kVp, and let's say we set a technique of, we're shooting a hand, a foot maybe, let's say 2.5 mass. Okay, so again, we're on a relatively new X-ray tube, and so our brim spectrum looks something like this. Okay, so if then we change our mass, we're going to leave our KVP the same. You know, this represents KVP. The right-hand end of this represents KVP. If we change our mass to 5 mass, and understand, y'all, there's no world in which I'm going to draw this to full scale, right? There's also no world in which I'm going to make these perfectly parallel to each other. So just understand that. So what does, again, this represent right here? It's average, right? So again, we're at 60 kVp. So the peak of the bubble represents average, which is right around 20 kVp, right? That's 1/3. And then all this under here represents intensity. You can call it mass at this point. I'm just going to call it numbers. Okay, it's just the number of X-rays that we create. So what did we do when we went from 2.5 mass to 5 mass? I'm screwing this 5 up. Something awful. 5 mass. All right. So we doubled it, right? So what's going to happen to our peak energy? Stays the same. Stays the same. So what is that? Not mass, right? So what does this control? Peak energy, right? So in this, it's just peak energy. Okay, so that's peak energy, that's KVP. What we're talking about is this right here. So what's going to happen, before I get there, what controls the minimum energies? Yeah. Filtration, all right, filtration. All right, so as I change my mass, what happens to my filtration? Trick question? Nothing. Nothing. All right. So what we're left with then, as we change our mass, we didn't change our KVP, we didn't change our filtration, so our minimum energy is going to come off at exactly the same spot, right? Our maximum energy is going to end at exactly the same spot. And all I'm going to get, I'm going to try to not mess up my marker and go directly over that, is that we just get an increase in numbers. And that's it. Nothing else changes when we change our mass. So the height of the bubble goes up. The average energy remains the same. The level of the minimum energy remains the same. And I'm saying that way for a specific reason. Do you get more minimum energies? Or more minimum energy X-ray photons? Absolutely you do. But where they come off down here, the energy level of the minimum energy X-ray photons does not change. Okay? And because of that, the average doesn't change. So the only thing that happens is we get more. We get more of everything, okay? So what do we call mass? Intensity. All right, so with filtration, we got increase in average and a decrease in intensity, which is strictly numbers, right? So effectively, we got a decrease in mass, but it's really just numbers. So with mass, if we increase our mass, then we get no effective change on minimum energies, no minimum, no effective change in average, no change in peak. The only thing that we affected was numbers, right? So what we got was an increase in the height of the bubble, and that just represents the numbers. That's the only thing it represents. Nothing else, all right? So why do we use mass to control our output, our tube output? Because the only thing that changes is numbers. Why do we use mass to control the output from the tube when we change from asthenic to sthenic patients? What do you need? More numbers, right? Right. So, the only thing that mass controls is numbers, right? Output from the X-ray tube. You lose numbers at the image receptor. You want to replace those numbers at the image receptor. So you change numbers, which is intensity, which is mass, right? So tissue differences, okay? You go from a patient who's got healthy lungs to somebody who's got a massive pleural effusion, okay? What's pleural effusion? Fluid, right? Fluid is fluid. So your compensation for that would be more numbers. Exactly. They're going to absorb more, so you're going to have more numbers. Now, understand, I'm going to totally screw this up in a minute. Intentionally, I'm going to totally screw this up because I think we should be doing something different. But anyway, more on that in a minute. And I'm going to tell you what to answer on the test, okay? Because this is just my opinion and where I expect that technique compensation is going to go within your career, probably within the next 10 years. But for right now, it's just numbers. So what is a pleural effusion? It's fluid in the lungs, but what is that? It's a pathology, right? So generally speaking, when we're compensating for pathology, what do we want to use to compensate for that pathology? Mass. Just more. Yeah, in pathologies, you've got two things. You've either got an additive pathology, which adds patient, I don't want to necessarily say density, but it adds more to the patient, which is going to make you lose photons, so you need to increase your, or it's going to be destructive. And in destructive, what you do is you remove absorption from the patient, so you get more penetration through the patient, more exposure at the image receptor. You want to reduce that at the image receptor, so you would reduce your, again, mass. Okay, so generally speaking, when we're talking about changes in technique for pathologies, most of the time your compensation factor is going to be mass. It is generally 30 to 50% change. Okay, so the other things that will affect output from the X-ray tube, I'm intentionally skipping over KVP because KVP is going to screw all of this up because KVP is just massive in context of patient exposure, in context of emission from the tube. So the other thing is a change in generator type. Now, this comes with the understanding that you're never going to change generator type. If you're shooting on a high frequency machine, you're shooting on a high frequency machine. Now you may have two rooms side by side that may be of different generation, and they're going to shoot a little bit different. You're probably never going to use a single phase machine unless you go to work in a hospital, not a hospital, but a doctor's clinic, and they just have a leftover machine from years gone by. But if we have a single phase versus a three-phase machine, okay, so with a single phase machine, what you know about single phase machine, we're still shooting at 60 kVp. Mass is irrelevant at this point. What you know about a single phase machine is that it's gonna be fully rectified, so it's gonna be full wave rectified, which means your voltage waveform looks like that. So what this represents is 0 kVp. And what this represents in this illustration would be 60 kVp. So you're already starting off with an X-ray beam that drops to 0 quite a bit. Does that make sense? You with me so far? When you have a three-phase machine, and it's also going to be fully rectified, what you're going to have is overlapping pulses, right? And with those overlapping pulses, your overall voltage waveform, even though each pulse is going to come to a 0, your overall output never does, right? So you've got three different generations of three-phase and high frequency. None of them are going to drop to 0%. So with a three-phase, you're already starting off with a higher average kVp. Okay, you with me so far? Okay, so then, I don't want to make that one and finish making the exposure. So then what we've got also is the output from the X-ray tube. Okay, so we get a higher average, right? So since we don't go from 60 to 0, 60 to 0, 60 to 0, with every pulse, we get a higher average. We eliminate all those zeros, okay? That's number one. Number two is that when we change from a single phase to a three-phase machine, we have to change our technique. You remember what the compensation for that was? Don't make me go, eh. Somebody almost said it, I think. Okay, sort of. If we go from single, oh, yeah. You're right, you're absolutely right. You go from single phase to three phase, you have to cut your mass in half. Why? Because each one of those pulses overlaps, right? If the pulses overlap, then that is going to give us a greater number. So with single phase to three phase, we get an increase in intensity. Also, because we never drop to 0, our voltage potential never drops to 0, then our average goes up, right? So we get an increase in intensity, we get an increase in average. Okay, so what represents average? Well, the kVp is going to affect it, and we'll get there here in a minute. But what represents average? The very top of the peak of the bubble, right? So when we're comparing a single phase to a three phase, and again, the peak of the bubble, just know this and don't get worked up about the difference in the actual number between single phase and three phase. Just know that statistically they say that the average X-ray beam is around 30% of the peak energy, or 33%, 1/3 of the peak energy, just to keep our decimals and fractions right. So single phase is going to be slightly lower than that. Three phase is going to be roughly 1/3. So if then we go from single phase to three phase, what controls our minimum energy? Right? What controls our peak energy? kVp, right. So what's the effect of going from single phase to three phase on either one of those two? Nothing, right? So, but we get an increase in intensity. Intensity is represented by numbers. So what's going to happen to the height of the bubble? It's going to go up. Right. And that looks really bad. But since our voltage waveform, our potential never drops to zero, then we're going to get a slight increase in the average, so the average increases as well. So what happens is the bubble goes up and it pushes towards the high energy side. Okay, so to review, because these are the two that you're going to confuse the most. With filtration, as filtration increases, your intensity decreases, pushes to the high energy side. So what do you have to do with your mass as you increase filtration? You lose numbers, you have to add numbers, you're going to increase mass, right? So as you increase mass, then the only thing that you affect is numbers, so the bubble goes up, right? As you go from single phase to three phase, then what's going to happen is you're going to get an increase in intensity, increase in numbers, the height of the bubble goes up, and it pushes towards the high energy side. Okay? Okay with those three? Anybody have any questions on this?
Will there be graphs on the test that we have to read?
There are, I think there's one question on the test, and we actually talked about that last week and how to identify something specific about two Brim spectra, and we're going to talk about it again here in just a second. Okay, so yeah.
Okay, I'm confused, because on both the filtration and the one phase to three phase, you said the bubble goes up and the average increases.
The filtration, the bubble goes down.
Oh, it goes down.
And that's why I wanted to stop here, because that's where you're going to have troubles, is because here in a minute we're going to talk about KVP and the bubble goes up and towards the high energy side. So you're going to equate push towards the high energy side with bubble going up. But with filtration, the bubble goes down. Yeah.
And then also.
But it pushes towards the high energy side. Yeah. Okay. Anything else? Because KVP is going to screw all this up. All right, so KVP. All right, so our technique again is 60 KVP. So we're at 60 KVP. All right, and understand this is Brim spectrum. Understand some words too. So Brim spectrum, you know, especially at creation, you know, at the face of the target, it's kind of like analog. You know, what you've got is an absolute continuous swoop curve that goes from the minimum energies to the maximum energy. It's continuous. As opposed to the characteristic spectrum only occurs at specific intervals. And we'll talk about those intervals here in a minute. But it's more than just 69.5. There's more characteristic X-rays that we'll create with a lot of different energies just to kind of explain it. But the only one we're interested in is 69.5. So with the Brim spectrum, we're going to call it continuous. But with the characteristic spectrum, we'll call it a discrete spectrum because it occurs at discrete levels, at specific discrete levels. Okay, discrete spectrum, characteristic, continuous, Brims. Okay. All right. So with KVP, if we increase our KVP, and we're going to say we're going to increase our KVP to 90 KVP. All right. So we're going to go 60, and I'm going to draw this on out and say 90 is right here. Okay. So what have you learned about KVP? Spit it out. What have you learned? It's the peak energy.
Penetration.
Right. It's penetration, it's peak energy, it's penetration, And it's the potential difference in the X-ray tube. It's the speed of the electrons that travel across the X-ray tube, smack into the target, lose more energy, you get a higher peak energy, right? So the difference between a 60 and a 90 kVp X-ray beam is that we just add 61, 62, 63, 64, 65, all the way up to 90, right? Not even close. Not even close. All right? So what's going to happen, because we're firing these things at a much higher rate of speed across the X-ray tube, is that we don't have more electrons coming across the tube. The number of electrons is controlled by mass. All right? But they're carrying more kinetic energy with them. All right? So they may penetrate a little bit deeper inside of the anode and interact with more atoms. But what do they have if they're traveling with a higher velocity? What do they have more to lose?
Energy.
Energy. They have more energy. So if they lose more energy, then we're going to get closer to the 90 kVp, right? So we can't create a 90 kVp X-ray photon if we set 60 kVp unless our machine is really messed up, right? Just not going to happen. So we send them across with 60 kVp worth of energy. That's the highest we're going to make. So if we increase to 90 kVp, now we can create a 90 kVp. So if I increase, let's do this. If I decrease from 60 kVp, our brim spectrum down here is not going to change. Our average is not going to change. What's going to happen is, let's say I change that to 55. That's what I'm going to get at 55 kVp. Now take that the opposite direction. What's our brim spectrum going to look like if I increase to 90 kVp?
Higher.
Bingo. That's one. What does the height represent?
Average number.
Yeah, numbers. Numbers. So what have we been telling you controls numbers? Mass. Mass, right. Does kVp control numbers?
Mm-hmm.
Oh, yeah. Yeah, much more so than mass. All right? So what we're going to get is we get an increase in numbers. Okay, so notice the minimum energy didn't change. Minimum energy didn't change because minimum energy is controlled by filtration. That's the only thing that's going to change your minimum energy. So we said that the average energy is roughly a third. So if we just make that blanket statement that the average energy is 1/3 of the peak energy, do we suspend that when we increase to 90 kVp? Answer is no. So we get an increase in numbers, and the increase in numbers is staggering. So we get an increase in numbers, we get an increase in average. Average now is 30 kVp. Difference between 20 kVp and 30 kVp is significant, right? 10 kVp is significant. But what we're going to get is a tremendous increase in numbers. But wait a minute. Mass controls numbers, right? Yeah, it does. Mass controls numbers. But does kVp control numbers too? Yeah, absolutely does. What else does kVp control? So at 60 kVp, what are we not high enough to get to? The characteristic spectrum. Right, so I know that there's a question on the test that is similar to this. Well, it doesn't have any numbers on it. It just says, what can you tell me about this spectrum versus that spectrum? And your answer would be? Because that spectrum has a characteristic spike, it's above 69 kVp. So between those two, which is a higher energy X-ray spectrum, or X-ray beam, it'll be that one, okay? So with kVp, what we get is, the floor changed. No change in minimum energy, because that's all filtration. We get an increase in numbers, we get an increase in average, and we get an increase in peak energy. Okay, so historical perspective. Why do we want to use mass instead of kVp? Well, what does kVp control in the patient? Controls, say again?
Attenuation.
It controls attenuation, right. So at 60 kVp, think of the exams you shoot with 60 kVp. What are they? Hand, feet, toes, fingers, thin stuff. Ever shot an abdomen with 60 kVp?
No.
Nah, hope not. You might have made that mistake, but I hope not. Okay, so for that thicker stuff, you're gonna need more power to get through the patient, right? So you're gonna have to increase your kVp. Okay, the downside to increasing kVp is that you get more penetration, but you get more equal penetration. You shoot that hand with 100 kVp, and what you get is tremendous penetration of the bones. What do you want to see when you're shooting hands and fingers? The bones. You need that contrast. You need that differential absorption. Differential absorption, it sounds complicated, it is not. It's different absorption in different tissue types and thicknesses. Differential absorption. Okay, so what controls your differential absorption is kVp. You increase kVp, you get less differential absorption, you get more penetration of more tissue types more evenly than at low kVp. Okay? Now, again, the historical context of this is that before we used computer processing to really give us our contrast, that's what we use to control contrast, is kVp. Okay? Also with kVp, what do you get more of in soft tissue? Amy probably covered this in intro. What emissions from the patient, not from the x-ray tube, but from the patient, do you get more of with increased kVp? Scatter, right. So now we're back to our abdomen. What is your abdomen composed of? Mainly soft tissue, right? So when's the last time you shot a KUB at, we'll say 100 kVp? Probably never, right? Unless you were doing barium work or something like that, you probably use something more like 80, maybe 85 kVp, right? Possibly even lower than that. Why? Because with higher kVp, you create more scatter. In both of those cases, with decreased differential absorption and more penetration, historically what we got was lower contrast. With more scatter radiation, likewise, we get lower contrast. So, you shoot, again, before we used computer processing, you shoot a KUB even on a small patient at 110 kVp, 120 kVp, is great for the patient. Because the higher the kVp, the more penetration, and what you're more or less absorption inside of the patient. And what you're going to learn next semester is more of that photon or more of that beam that absorbs inside of the patient, the worse it is for the patient, the more dose for the patient. So from a patient dose perspective, the higher the kVp that you use, the better off. But from a historic imaging standpoint, and again, I'm saying before computer processing, the worse the image. Well, what are we trying to do? Get a good image on the patient so we can make a diagnosis. You create crappy images, and what's your diagnosis rate like? Equally crappy, right. So we used lower kVp, okay? So kVp touches everything. It touches the average energy, it touches the peak energy, it touches the numbers, it touches everything in the X-ray beam. All the imaging characteristics in the X-ray beam are affected by kVp. So we wanted to keep kVp relatively constant for exam types, fingers and hands, toes and feet. We're going to be very low kVp, get thicker, increase kVp a little bit because it's thicker. But for the most part, the technical factor of choice for most changes was going to be mass, yeah. is going to be mass before digital processing. Okay, now this is the part that I want you to just understand, that I think this is where this is going to go. This is the stuff you have to know, okay? This is the stuff you have to know. As KVP goes up, you know, we get a higher average, pushes towards the high energy side, we get an increase in peak, we get an increase in numbers, it affects everything. But where I expect things to go, you know, there was a push a few years ago. I think it was called the Image Gently initiative. And what they were trying to do is bring more focus to X-ray quality, using proper technical factors, collimation, all this kind of stuff. All right, and the intent was to try to bring patient dose down as much as possible. And that all occurred right around the time we were making the shift from non-digital to what we refer to as CR. That was first incarnation, or the easiest transition from screens and films to some sort of digital processing. The reason it was the easiest is because the only thing we had to do, you know, the image receptors were identical. The inside of the image receptor was a little bit different, or quite a bit different, but the appearance from the outside was identical, and the processor looked just like a processor from film. So it was kind of plug and play. Got rid of screens, got rid of films, and put this other thing in place, and we just kept chugging along. And what happened though is that, and Amy may have touched on this, is the CR cassettes, the image capture was half as efficient as what it was in screens and films. Meaning that what we had to have was twice the dose to the patient in order to get the exact same quality image. Okay? So that was a concern. You know, we're double dosing the patient for the convenience of using this technology, but once we went to what we have now, which is DR, the sensitivity returned to the same or even more sensitive than what it was with screens and films. Okay? So what happened was that when we went from screens and films, since the dose doubled to the patient, we had to use twice the mass. And so we don't want to do that. We don't want to do that. We don't want to give the patient twice the dose. So now we're stepping back into Amy's class for a second. Okay? So what is the 15% rule? It's changing KVP. If you increase your KVP by 15%, you can maintain the image receptor dose by decreasing your mass by a factor of 2. Okay? Now, suspend the decrease in mass. Okay? If you increase your KVP by 15%, what happens to your image receptor dose if you do nothing with mass? It's going to increase by a factor of 2. That's why the 15% rule, if you increase by 15%, you reduce your dose, or you reduce your mass by a factor of 2, is because a 15% increase in KVP equates to a 100% change in mass. Okay, so now, again, back to what I was talking about before, in dose to the patient, what's a better dose to the patient? Is it increased KVP or increased mass?
Increase KVP.
Increased KVP, right, right. So instead of doubling the mass, what we did was we increased our KVP by 15%. Okay, so I walked a long way to say, if we did that with screens and films before digital processing, what would happen to your image? Right? Because differential absorption goes down with increased KVP, scatter goes up with increased KVP, you're going to lose contrast. But that's old technology that we don't use anymore. With the digital processing, what controls our contrast is no longer KVP. It's that digital processing. So I know Amy talked to y'all about histograms, right? So the way a histogram works is that if you can get deep enough into the computer system, what you'll see for every exam type, you know, or the histogram that you create whenever you shoot an image, is you'll see this graph, and it won't make any sense to you at all. It's just this set of lines that are vertical, right? So these vertical lines represent the scale of contrast that your image or the saved histogram, the lookup table, represents, okay? So when you get a new machine, what they'll do is they'll go through all exam types the radiologist is gonna look at, and they're gonna ask them, you know, which one of these 4 or 5 images looks the best to you, and he's gonna pick that out. That image is represented by a specific histogram that is the lookup table for which all of those exams of that same type will be compared to and adjusted to for contrast and density. All right, so let's say they're all lines, right? And let's say our ideal histogram has lines that are, let's say this far apart. You make an exposure and you use the wrong KVP, and your lines are like this, okay? We've got a process in the computer system, it's called what they refer to as automatic rescaling. And automatic rescaling is taking your busted up histogram and trying to make it look like this one. So what it's gonna do is kind of superimpose the two, and it's gonna adjust it to where they come together. And now, even though you used way too much KVP, you really can't see a difference. You can't see a difference. You can test this. You know, you can go into clinicals and you can shoot, you know, if you've got a skull phantom, take that skull phantom, I don't mean a plastic one, I mean one of the real ones. Take that skull phantom and make an exposure on it at 50 kVp. Phototime it, so you don't have to worry about mass. Phototime it at 50 kVp, then phototime it again at 100 kVp, and look at the two images side by side. The difference will be minimal. Now, I'll walk a long way to say that. Is there really any reason for us to be increasing if contrast isn't gonna change with changes in KVP? Is there really any reason for us to be using mass to adjust for pathologies? If the patient has a massive pleural effusion, what do you think is gonna happen to the dose to the patient? Now, you replaced air with fluid,
Increase it?
it's going to increase it quite a bit, right? So if you increase mass, you just get dose to the patient, right? So if you increase KVP, are you going to get dose to the patient? You are. Dose is going to go up, but is it going to, say, a 10% change in KVP? If 15% change in KVP is equivalent to doubling in mass, what is 10% change in KVP? Not double the mass,
Yeah.
right? Right? Make sense? So why are we not using KVP to compensate for tissue thickness, exam type, pathology, everything? Why are we not using KVP? I'm asking honestly, because I have no freaking idea. I have no idea why we're not. Okay, so this is what I expect is going to happen eventually in your career lifetime, is that there's going to be a shift. You know, people are going to wake up and say, you know, KVP does not affect contrast in a digital world enough to really be too concerned about it. And when that happens, textbooks are going to change, practices in the hospital are going to change, and mass is going to remain relatively constant while KVP becomes your technical factor of choice to compensate for those things. So suddenly you're going to be shooting KUBs at 100, 110, 115 KVP because it doesn't affect contrast all that much. Chest x-rays, you know, again, you're not going to want to hear that loud crack on your machine if you increased to 150 kVp, so you're probably going to remain at 120 kVp for chest x-rays. Hands, 65, 70 kVp. Feet, 75, 80 kVp. Mass is going to go through the floor. Patient dose is going to decrease because we're going to start doing what we should already be doing and increasing KVP. Okay? All right. So the other thing, well, while it's in front of me, if you look on page 137, this is figure 8.9. What you see in each one of those spikes are possible characteristic X-rays. Okay, so the reason there's so many of them is because you can create a characteristic X-ray off of any shell. You knock any electron out of its orbit, and it's going to be replaced by a different one, and you can get a characteristic X-ray beam off of that. Okay, so the tightest bound are the K-shell, so if you knock that out and you replace it, it's held in place with 69.5 keV. If you replace it with a free-floating electron, then the energy level of that K-shell interaction is going to be the difference between 0 and 69.5, which is going to give you, that characteristic 69.5 kVp X-ray photon, right? But the L shell, it could pull one in from the L shell. So if it pulls one in from the L shell, okay, so we're just going to say 69. The L shell is roughly 12 keV worth of energy. If you knock out the K shell and you replace it with the L shell, again, it's the difference between the binding energies between 12 and 69. That's going to give you a 57 kVp X-ray photon, right? So we're going to create, and then the next one out is like 0.3, so that's going to give us almost 69. So we're going to create a lot of X-ray photons that are characteristic, but the only one that we're going to pay attention to is the 69.5. Okay, so that's what that chart represents, are the X-ray photons that we can create, the combination of X-ray photons that are statistically characteristic photons, just not ones that we care about. Okay? So then the target material, if you look on page 141, the target material, you change everything. Tungsten is the best that we can use, the best target material we can use for diagnostic. That's because it's got a big nucleus, a lot of electrons, most efficient for diagnostic X-rays, departmental X-rays. If you could use something with a atomic number similar to gold, then what we would get is a higher energy, higher average, higher output. Everything would go up. Can't use gold, melts too easy. But in mammo, we use molybdenum. So molybdenum has a significantly lower atomic number at 42. So if you look at the characteristic curve of molybdenum, then you see that we get a decrease in output and a decrease in average, right? So the target material, if you see a graph where you see a number of different lines like that, and they say, what do you know about these? And this is not on my test, but if you see it on a registry, what do you know about these different, brim spectra? Well, molybdenum is at the bottom of that. Tungsten is, where it is with the 69.5 characteristic discrete spectrum. So that's what the change in the target material will do, is it will change everything except for the peak energy and the minimum energy, because peak energy is controlled by one thing only, and that is kVp, right? Minimum energy is controlled by one thing only, and that is filtration, right? So I don't think that there's anything in chapter 9 that we haven't already talked about. The math in chapter 9, mass and X-ray energy, kVp and X-ray energy are, it's not on there. Something that you may see, definitely will see next semester, is the effects of kVp on output. So what we get and really all of this, the effects of KVP, well, the effects of, let's say, filtration on tube output, that is intensity, as it decreases, it pushes it towards the high energy side, increases the average. For mass, it's a one-for-one thing. You double your mass, you double your output, and that's the only thing it affects. With machine phase, you get an increase in numbers by a factor of 2, and it pushes it towards the high energy side, you get a higher average. With KVP, again, it touches everything, increases the maximum, gives you a characteristic spectrum, increases the average, and here's the thing, it increases the numbers, but it increases the numbers directly and exponentially, okay? Where mass only increases numbers directly, KVP increases numbers directly and exponentially. What does that mean? Well, directly means you increase one, you increase the other, right? Inversely would be the other way around. So, you know, you got an inverse relationship here. It's direct here, here, and here. So it increases directly, meaning you increase your KVP, you increase your output. But it's exponential. What does that mean? Yeah, as a whole multiples, right? So 15% equals 100%. That's exponential, right? 15% increase in KVP increases your tube output, your numbers, by 100%. And that's why the 15% rule works the way it does. Increase KVP by 15%, reduce mass by a factor of 2, you maintain the image receptor exposure. Okay? Questions?